and we have a really special talk for you tonight. Somebody who just popped up on my email saying, "Oh, I'd love to give a talk," and I was like, "Oh, this is great! This is fantastic." We have Dangerous Worlds by Elizabeth Tasker, and I'll tell you a little bit more about her later. Our website for more information, if you go to your favorite browser and put in Hubble Public Talks or Hubble Public Lecture Series, you can't say space, you could say Space Telescope probably, but Hubble is the word that usually gets you here. To all this with the list of the upcoming lectures, the how to watch live online. You can watch the past lectures all the way back to 2005, so that's 12 years of astronomical goodness for you. And you can also sign up for our email list, or if you think it's that one or two emails a month is too much, you can also unsubscribe to them. All right. Let's see, the announcements, sign up at the website, or if you are old-fashioned, you can just give me your email and I'll make sure you get added to the list. If you have comments or questions, send them to publiclecture@stsca.edu. It'll come into my mailbox and we'll make sure we get your question answered, okay? Let's see, social media, Facebook, Twitter, YouTube, Instagram. There's a lot of those. If you would like to follow Space Telescope, we are available on various social media. I myself have Facebook, Google+, and Twitter, but as I say every month, I'm only so often on there because I've got lots of other things to do. And I do sometimes a blog on Hubble site if you want to follow me. Unfortunately, the weather is not permitting tonight. To those of you who brought the umbrellas in, no, definitely not permitting. And unfortunately, the observatory is not permitting. The observatory is closed for repairs until further notice. They had some problems with their dome, and they emailed me today that they don't know when they'll be able to reopen. So you can go to md.spacegrant.org. You will find this web page over here on the right. And the observatory status will not say check back on Friday. It will say that check back next month or in a few weeks, and we'll be able to tell you when the repairs will be done. Okay? So unfortunately, for the next couple of months, possibly, we will not have the Maryland Space Grant Observatory. Okay? All right. Now our news from the universe for November 2017. The first story tonight. A wrinkle in space-time. As you know, I like to make small puns here. This, of course, is playing off Madeleine L'Engle's famous story, A Wrinkle in Time. And what I'm talking about, of course, is the LIGO project, the Laser Interferometer Gravitational Wave Observatory, which I told you about early last year, has these two detectors, one in Hanford, Washington, one in Livingston, Louisiana. And you can see they are these big, long arrays that they send laser beams down, each one of them, and the laser beams bounce off a mirror and come back, and they measure the distance very, very, very accurately so that when the distances change, they could tell by an incredibly small amount. And they did measure an incredibly small amount of change in, let's see, when was this observation done? It was, I can't remember the exact date of this observation, but this was the detection of a black hole merger. That was about 1.3 billion light years away, the first detection of gravitational waves. And it was seen, here is the data versus the predicted for Livingston, and same for Hanford. In fact, it was detected in both of them, and with the proper time delay for the light to travel between them, first detection of gravitational waves. And on October 3rd of this year, it was awarded the 2017 Nobel Prize in Physics to these three gentlemen of the LIGO-Virgo collaboration for the decisive contributions to the LIGO detector and the observation of gravitational waves. Now, we all sort of knew this was going to come because, I mean, you detect gravitational waves for the very first time. Yeah, that's worthy of a Nobel Prize. I personally did not expect it to come so quickly. All right, but, you know, since the discovery of those first black hole mergers, they've discovered 3 or 4 more black hole mergers, so they're getting more observations. But last summer, on August 17th, They also saw a neutron star merger. Okay, so black holes are even all right. So a star can end up in several different ways. Okay, a medium mass star, low mass star ends up as what's called a white dwarf, and that's about the density of the atom. Okay, and it's supported by electron degeneracy pressure, yada yada yada. But it's about the density of an atom, about the size of Earth. Okay, all right. And then there is if you are more massive, you can collapse down to what we call a neutron star, which is about the density of an atomic nucleus. Okay. And that's about the mass of the sun compacted to about 10 kilometers across, or about the size of the Baltimore Beltway. Okay, so take all the sun, compass it down to the Baltimore Beltway size, a 10-kilometer across, and that's when you get a neutron star. A black hole goes even further than that, is even more massive, even higher density. Okay, so these neutron stars, when they collide, they're incredibly dense. When they merge together, they will also produce gravitational waves, but not really as strong as a black hole. But this neutron star collision was only 130 million light years away, which I know sounds pretty far, but compared to the 1.3 billion light years away that black hole merger was, is actually only 10% of that distance. So they were able to see this neutron star collision with LIGO and Virgo. Virgo is the European version of LIGO. However, what made it even more exciting is it also was observed in optical light. Using both the LIGO detectors here in the US and the Virgo detector in Italy, they were able to relatively accurately determine where it was on the sky. And astronomers were able to search for that point on the sky and found that there was an excess of radiation coming from this dot within the galaxy NGC 4993. So they actually were able to do follow-up observations. And neutron star collisions will have a lot of material around them, and it will generate a lot of optical light. Okay, so this is Hubble's observation from August 22nd through August 28th, over 6 days, watching the neutron star, the light from that collision fade away. All right? And it's not just that it was seen by Hubble. Matter of fact, Hubble was not the first one to see it. It was actually first seen by Fermi in gamma rays. So it was seen in gravitational waves by LIGO and Virgo. It was seen in gamma rays by Fermi, Integral, and Swift. It was seen in X-rays by Chandra. It was seen in visible light by Hubble. It was seen in infrared light by Spitzer. And it was seen by visible and infrared light by things like Pan-STARRS and other ground-based observatories. So this is when astronomers can really get to work, when they can really characterize the event. When we see it in this many different wavelengths, we see what's happening at lots of different energies, and we can understand the event a lot more. The black hole merger that won the Nobel Prize, there were no follow-up studies. We didn't see it in any other wavelengths. This neutron star merger, we were able to see in other wavelengths. We're able to get different characteristics of it, and we're able to understand the processes that are going on. And the basic result so far has been that, hey, it sort of fits what we think happens, which is actually kind of crazy, okay? Because we have these ideas, and we say, all right, well, this is our prediction. So we usually expect to be surprised by, nature behaves slightly differently than we predicted. Most of the predictions seem to be working out pretty well for this. Although there was one thing in terms of seeing it in ultraviolet that they didn't expect, and the fact that it was a relatively faint gamma ray, okay? It's a short duration, but it's a faint gamma ray burst, okay? These short duration bursts for something so close should actually have been larger, and they're not quite sure why. But these are all the questions that come up when you have this many different ways of looking at it and are able to study it in so many ways. So this, not only have we moved into gravitational wave astrophysics, but we've got follow-ups to be able to correlate it, which makes it so much more valuable. Our second story tonight, on the trail of asteroids. Now, Hubble had this amazing project called the Frontier Fields, okay? And the Frontier Fields looked at 6 really massive clusters to look for gravitational lensing. So this is the massive galaxy cluster Abell 370. And all these streaky things in here are gravitationally lensed arcs, okay? And we've talked about that a lot. And at the same time, while they were doing while they were looking at the galaxy cluster, they also looked at what they called parallel fields. So one detector of Hubble was looking at the cluster, another detector was looking at the parallel field. And then actually they rotated, and then that one detector looked at the parallel field and the other detector looked at the cluster, okay? And they spent about 100 hours of observation time on each of these clusters. Well, these are the cleaned up images that you see, okay? And of course, the real observations have lots of, cosmic rays and other things that have, and, detector artifacts that have to be cleaned up. But there's also another thing that they had to clean up out of these images that is illustrated by this movie. So as this movie plays, you'll start to see these little streaks appear. And they're numbered 1 through 7 because these are 7 unique asteroids that pass through the field over the 100 hours that Hubble was observing. Now, Hubble doesn't observe it continuously. It does a bit of observation, and then it'll go off and do something else, and it'll come back to the field and do some more observation, etc. Which is why number 7 here, you can see, is split into 4 separate little loops. All right, and why are they streaks and curved loops? Well, Hubble and Earth are moving relative to the asteroid while we're taking the observations. So the asteroid actually ends up streaking, and the parallax motion produces that little curve on there. All right? So for Abell 370 and its parallel field, here are the cleaned up images, and there are the images with the asteroid streaks. Now you'll notice we use the movie on the parallel field simply because there are already these streaks in the gravitational lens. Those are actually galaxies that are beyond the gravitational lens. But if I blink back and forth, you can see the asteroids and where they appear in the field. And this is kind of cool because what you've got here in one image is you've got some things within the solar system as well as you've got things that are billions of light years away. And it reinforces one of the things that we have to deal with in astronomy. When you look out into the universe, it's the sum of everything that you're looking through, the solar system to the galaxy, to the distant galaxies, all the way to the edge of the universe. That when you take an image, you're combining all of that into one of those. And here you can see some of the nearest things and some of the farthest things in the universe all combined together. That's kind of cool. All right. So now we'll go to our featured speaker. And our featured speaker tonight, let's see if her laptop takes over. Yes, it does, is Dr. Elizabeth Tasker. And she is originally from the UK. She did her undergraduate work at Durham University and then did her graduate work at University of Oxford. Then she came across to the United States and Canada and did some postdoctoral work here before going even further from home, where she is an associate professor at the Japan Aerospace Exploration Agency. And I love JAXA because it's a great acronym to say. It's like NASA, but it has sort of an intriguing sound to it. JAXA just sounds as good as NASA in terms of a space agency. She does her research work on the formation of stars and planets by doing computer simulations. And today is a very special day for her because she has a book that is being published today. And I'm sure she'll mention that in her talk. Ladies and gentlemen, Dr. Elizabeth Tasker.
Well, thank you very much. Am I good? Hello?
It is green, so.
It's green. Okay. So today I'm going to be talking about planets, especially those beyond our solar system. But I'm going to start with what I hope is a vaguely familiar image. Well, in a minute I'll be starting with what I hope is a vaguely familiar image. There we go. So I hope these guys look somewhat familiar to everyone. And I say this is the sun. And then just past the sun, we have our 4 smallest planets, Mercury, Venus, Earth, and Mars. And just past Mars, we have this band of rocky leftovers from the planet formation process that we call the asteroid belt, which also contains the dwarf planet Ceres. And then beyond the asteroid belt, we have the giants, Jupiter, Saturn, Uranus, and Neptune. And then we have this another pile of rocky leftovers from planet formation, which is the Kuiper belt. And of course, its most famous member is the dwarf planet Pluto, though we never really talk about that anymore. And you are here, all right? So if you were to base all our understanding of planet formation on our solar system, we would note that you have two types of planets. You have rocky planets, so these guys, Mercury through to Mars, and here you have a solid surface with a relatively thin atmosphere. And then beyond the asteroid belt, you have gas giant planets, where most of their volume is taken up with their atmosphere, around a much smaller, dense central core. And this colossal atmosphere results in absolutely crushing pressures near their core. So much so that, in fact, hydrogen on Jupiter, by the time you approach Jupiter's core, it becomes so dense that it starts behaving as this kind of metallic compound. So until 1990s, these were all the planets we knew. And we didn't think that our solar system was the only one out there, but we hadn't actually seen any others, so nothing was definite. But then everything changed. So our sun is one of about 100 billion stars in the Milky Way galaxy. And when we talk about extrasolar planets, we mean extra as in outside, and solar as in the sun. So an extrasolar planet or exoplanet is any planet that is not in our solar system. And the story of extrasolar planets begins in 1990, when the Arecibo radio telescope in Puerto Rico was in need of repairs. The repairs, however, were actually structural cracks. So around the same time, a similar radio telescope in Green Bank in the US also had structural cracks, which were ignored, and the whole thing collapsed. So in a fit of panic, Arecibo was like, okay, we've got the message, we're going to fix this. But during repairs, the telescope was not taken completely offline, but it couldn't be moved. So typically during a night, the telescope will move very slightly across the sky as it tracks objects. But during these repairs, nothing could be done. It had to be absolutely stationary. And this made it unfit for almost all projects. However, at the time was a postdoctoral researcher called Alex Volshen. And he asked to use the telescope for a month-long survey, because this survey could be done while the telescope wasn't moving. And normally, such a proposal would never have gone through, because he required half the telescope's time, and this was the biggest telescope in the world for radio, so people would be like, yeah, no. But as it happened, no one else could really use it. He was based at the telescope, and they said, fine. And what Alex wanted to find were dead stars called pulsars. So actually, we've just had a very nice summary of these. Because a pulsar is what forms when a star that is much larger than our sun, more than 8 times, eventually reaches the end of its life and it runs out of fuel to burn. And when that happens, the star dies in a supernova explosion. And the bit that's left behind collapses to incredible densities, so dense that its atoms actually start to disintegrate. And the protons and the electrons inside the atoms merge to become neutrons. And so we therefore call these neutron stars, which is exactly the same source of the gravitational waves mentioned earlier. However, as mentioned, these are tiny, so only city-sized, or indeed the Baltimore belt. And yet they weigh between 1.4 and twice the mass of the sun, so they're incredibly dense objects. And as they collapse, their magnetic field also strengthens a lot. And this magnetic field causes any remaining charges left on the neutron star to be ripped off and fired into the cosmos as powerful jets. Now, if these jets happen to swing by the Earth as the star rotates, then we see a periodic light pulse, and therefore we call these a pulsar. Now, the accuracy for these pulses is incredibly high. It's so high that when they were first discovered, they were thought that they might even be extraterrestrial sources. But in fact, when more sources were discovered across the sky, it was realized that actually a natural process must be causing these. But their accuracy is such that it rivals that of atomic clocks. Except for this one pulsar that Alex Volshen saw. So this pulsar was called PSR B1257 plus 12, that very catchy name. And for this particular pulsar, so PSR is pulsating source of radio, and then that completely unmemorable letters and numbers is the position in the sky. But for this particular pulsar, the time between the flashes changed very slightly. And it was ultimately concluded that this was due to two planets orbiting the pulsar. And as the planets orbited the pulsar wobbled very slightly due to the planet's gravity. And as it wobbled, its distance from the Earth was changing a tiny amount. And this was causing the flashes to have to travel slightly further and slightly less far. And therefore, their timing started to become off. So the discovery was two planets, which were, again, very imaginative, named PSR B1257 plus 12, B and C. And they were roughly 4 times the mass of the Earth. And their years, so their orbits around the pulsar, were 65 and 98 days. So for comparison, Mercury, our innermost planet, has an orbit of 88 days. So if these two were around our own sun, they would sit either side of Mercury. And they are a rather staggering 2,000 light years away, which tells you exactly how sensitive this technique was. Now, these were the first planets ever to be found outside our solar system. And the discovery was, appropriately enough, published in the international journal Nature on the 9th of January in 1992. However, it actually was leaked earlier than that by the British broadsheet newspaper, The Independent, on the 29th of October 1991, with the headline, "Radio Astronomer Finds 2 Planets in Distant Space." Now, Alex Volshen was approached by The Independent and asked for a quote. And this must have been fairly nerve-wracking because obviously he wanted this discovery to be published in a journal such as Nature. But if news gets out early, sometimes Nature might be like, well, it's no longer news, so we don't want it. So as a result, there's a very guarded comment by Alex Volshen here, saying Professor Volshen was not prepared to talk about his research because he feared it might prejudice the chances of being published in a scientific journal. However, despite this, even after the Nature publication, there was very little public notice, which when you think of the fuss that new discoveries have nowadays, where you have multiple reports against the whole world media, is very surprising that the first planets we ever found, no one really talked about. Indeed, at the time, my parents were taking The Independent, and this newspaper must have sat on our kitchen table, and I don't remember it at all. So what was the problem? Was it that just pulsar planets were just a bit too weird? I mean, you know, pulsars, dead stars, can't really relate to those. Hopefully never will be able to relate to those. Maybe people just didn't really feel a connection. So as a result, these were sort of overlooked. But pulsar timings, unsurprisingly, can only be used to find planets around pulsars. So what about finding planets around regular stars? So we found the pulsar planets because there was this slight change in the timing of the pulsar flash due to this wobble in the star's position because of the planet's orbit. So could we do this with normal starlight as well? And obviously the answer is yes, so I would not have taken us in this direction. So when you have a more regular star, you have a system like this. So here are we on the Earth. There's our star here, and here is our planet. And due to the planet's orbit, the star is going to make a small wobble. Now, as the star moves away from the Earth, its light that's reaching us is going to get stretched out. And this is going to cause it to become redder. Now, as it swings around the other side of its wobbling position, the light waves are going to become compressed as the star starts approaching the Earth. And when they get compressed, the light gets bluer. So what you see is this tiny shift from red to blue to red to blue as the star wobbles due to its orbit from the planet. And we call this the radial velocity technique, or sometimes the Doppler wobble technique. However, this is not a big shift. The tiny, tiny shift in light, and it's incredibly hard to measure. However, in 1988, a new technique was established. So in this technique, you have your star emitting light, and you've got your telescope. And in front of the telescope, we're going to put a jar of gas. And the point is here, that here is your star, and its light is going to be slowly shifting from red to blue. Tiny, tiny, tiny shift. But our jar of gas is also going to be emitting light that is not shifting, because it's completely stationary in front of our telescope. So what it is it's a bit like slamming down a ruler. And because you now have a stationary point with which to compare that starlight, it becomes much easier to measure tiny shifts. So this allowed us to have much higher accuracy when trying to measure this radial velocity change. And using this technique, as early as 1988, a wobble was seen around a star called Gamma Zephyr. Could this be from an exoplanet? So there were some problems. Gamma Zephyr is part of a binary star system, meaning it has a companion star, and the two stars orbit one another. So this was the first question mark. Would we even expect planets around a binary system? If you had a sister star, would that disrupt the planet formation process? Secondly, the star that was wobbling was thought to be a giant star. Now, this is the phase that stars reach near the end of their life. And as they approach the end of their life, they get quite crotchety. So what you find is the outer layers of the star start to have a lot of vibrations and pulsations that look just like a small wobble from a planet. So the astronomers were a bit suspicious. And in the end, they concluded, it's a giant star, it's a binary, we don't really expect to see a planet here. There are lots of other reasons for this possible wobble. No, we see a wobble, but it's not a planet. And when they announced that, they missed discovering the first exoplanet, because this wobble was due to a planet, but its discovery was not finally announced, I think, until 2013. So, the first discovery that actually everyone remembers is a planet called 51 Pegasus b that was found in 1995 with this same radial velocity technique with the light shifting from red to blue. And it was the first planet that was found around a star like our sun, rather than a giant star or a long dead star like a pulsar. And it opened the floodgates to finding thousands more, because it proved this radial velocity wobble was detectable, we could see it. And from there, we started discovering planets in droves. However, this planet was also rather strange. So back to our own solar system. And one thing that we note is that our giant planets, these huge gaseous ones, sit a long way from the sun. We have the rocky ones close, and we have the gaseous ones further away. But this planet, 51 Pegasus b, was a gas giant on the orbit of just 4 days. So if remember, Mercury is 88 days. That puts 51 Pegasus b really, really close to its star. So how do you form a planet there? Well, let's just take a step back and ask why this is at all surprising. So young stars are surrounded by disks of gas and dust known as protoplanetary disks. Now this image here is an artist's impression. However, this one is not. This is a genuine image of a protoplanetary disk around a young star taken with ALMA. And in this disk of dust and gas, dust starts off at micrometer sizes, and it starts to collide and stick. So we go from micrometer to millimeter to centimeter, up to meter sizes, and now we're starting to look a bit like the asteroids. And eventually, gravity finally gets seriously interested, and it squishes our newly formed planet into a ball, and we start to say, yes, okay, well, I acknowledge that's a planet. Now, there is one subtlety to this process that I'm sure will astound everyone. If you are forming near the new star, you're hot. On the other hand, if you're forming a long way away, you're cold. And this has one important effect. There comes a point as you step away from the star that ice starts to form. And we call this point the ice line, the snow line, or the frost line. If you are inside the ice line and closer to the star, water is a vapor. On the other hand, if you're the other side of it, then it is a solid. And that means you get a huge boost in planet-forming material the other side of the ice line. Because here you've got your silicates, like what the Earth is mainly formed of, but out here you've got the silicates, but also a huge number of ices. So you get a big step in density. It's like being given a whole new Lego set. So as a result, we expect small planets to form here, where we have less building material, and giant planets to form here, where we have a lot more. And this should be the same around every star, because the only assumption I've put in here is that you're hot if you're close to the star, which you think would be universally true. So, how do we get a planet here? There should be barely any building material there, and yet 51 Pegasus b was roughly the same size as Jupiter. So this is what we think happens. As the planet grows, it eventually reaches the size of Mars. Now, Mars is not a big planet. It is roughly 1/10 of the mass of Earth. But however, at that point, the planet's gravity gets strong enough that it starts to pull on the surrounding gas and dust that still circle the young star. And this gas and dust pulls back. And the result is like being on a running track. So here you are, and you're going to be running this circular race with two buddies, a bunny and a detective. And a little later on, oh no, I'm sorry, yes, there's been a terrible addition where for some reason you've been tied to your friends with a piece of rope. But a little later on, you're here. Now, your bunny friend was on the inside running track, and as I'm sure everyone remembers from school PE lessons, that gives you a very unfair advantage. So they're on a much shorter running track, and he's pulled ahead of you. On the other hand, your detective friend was on the outside running track and had further to go, and therefore she is a little bit further behind. But you're still tied together with this rope, so you start to feel a force with the bunny pulling you forward and the detective pulling you back. And the same thing happens due to gravity with our new planet in our disk, where the gas closer to the star is pulling ahead and dragging on that planet to move it forward, whereas the gas further out is pulling back and trying to slow that planet down. And as a result, you end up in this tug of war. And the net result is usually that the planet feels a push inwards. So what this means is, oh yes, and we call this migration. So what this means is your planet can start far out. It can form where there's lots of ice, there's lots of building material, and it can get big and Jupiter-sized. But it can then migrate inwards due to this pull from the gas disk. And when the gas disk is finally evaporated by the star, you end up with a large planet close to the star. And we call these hot Jupiters because they're Jupiter-sized and hot. So this explained 51 Pegasus b. But what about the pulsar planets? What could explain them, and were they even surprising? Well, the problem with pulsar planets is, as I briefly mentioned, pulsars start with an explosion, a supernova. So when they explode, if they still have planets orbiting them, two awful things can happen to those planets. The first is one can be vaporized. The second is the shock wave from that explosion can kick the planet out of the solar system. So generally speaking, we do not expect these planets to be able to survive this supernova explosion. So how on earth do you end up with a pulsar orbited by planets? Well, evidence to what might have happened was discovered in 2012, when a tiny star was found that seemed to be flashing red and then blue. And it turned out to be orbiting a pulsar every 93 minutes, which is actually the average commute time in the UK. But as this planet orbited the pulsar, you actually started to see different sides of it. So if the pulsar is here, and you are the Earth, first of all, you're seeing the front side. And the front side was being hit by the pulsar's jets and becoming very hot. However, as the star orbited, you started to see the backside, and this was much colder. So what you were seeing was intermittently the hot side of the star, then the cold side, seeing this flash from red to blue and back again. But because the pulsar was being hit, because the star was being hit by the pulsar's jets, the pulsar was blow-torching it to pieces. So you have a system a little bit like this one, where the pulsar's jets were ripping over the star and shredding it. And as the pulsar ripped this other star to pieces, a disk formed from its ruined body. And in this disk, planets could start to form again. So pulsar planets have rather a morbid origin. They require another star to be shredded to pieces and its broken body to form the birth ground of new planets. So these first finds were strange worlds. But later, we found many planets that were much closer in size to the Earth, orbiting around normal stars. Around now, we have found, I think, about 3,500 planets beyond our sun. And roughly a third of those have a radius that is less than twice that of the Earth. So this brings us to the obvious question. Can we find Earth 2.0? Well, let's look at what we know with an example that hit the news at the beginning of this year. And the telescope that made this news was a telescope called Transiting Planets and Planetesimals Small Telescope. And it's a 60-centimeter telescope in Chile. And if you take these letters very slightly randomly, you can spell TRAPPIST, which I'm sure entirely coincidentally, because it's a Belgian telescope, also happens to be the name of a Belgian beer. But in February, TRAPPIST made an incredible discovery. It found a star orbited by 7 planets. Now, as a telescope that made the discovery, the star was named TRAPPIST-1, and the planets became TRAPPIST-1 B, C, D, E, F, G, and H. So was this a solar system like our own? Well, the press got pretty excited. We had headlines like NASA's discovery of a solar system with 7 Earth-like planets will change how we hunt for alien life. We had from New Scientist exoplanet discoveries, 7 Earth-sized exoplanets may have water. Or from The Guardian, exoplanet discoveries, 7 Earth-sized planets found orbiting a nearby star. Clearly, if you just read the press headlines, you would think we'd found this. Clearly, 7 Earth septuplets, all identical, probably already have Starbucks on them. But what do we really know about them? Well, these planets were discovered not with the radial velocity technique, but with the transit technique. And this is when the planet moves in front of the star's surface and causes a tiny dip in the starlight, and it's how the Kepler Space Telescope finds its planets. So in the case of the TRAPPIST-7, we see 7 periodic dips as the planets pass by the star's surface. Now, transits usually they give you the planet radius, the physical size of the planet. So the bigger the planet, the more light it blocks out, and you can pick this up with the transit. It doesn't normally tell you the planet mass, normally. But the TRAPPIST planets were slightly different. So TRAPPIST-1 has many planets, it has 7. And as they orbit the star, the planets pull on one another. And as a result, they slightly change the time for each orbit. So this is like if you're running around your circular running track again, but this time you've taken your dog along for the run. And your dog is not always terribly cooperative. Sometimes your dog is pulling you forwards, and that means you make your lap time slightly quicker. But sometimes your dog just wants to sniff stuff, and it's pulling you back, and so your lap time becomes slightly slower. And these changes in lap time can be measured due to the planets pulling on each other. And we call this transit timing variations, or TTV. So I have a movie that demonstrates this. It's a little bit long, but it's quite cool. So we're going to start off with one planet orbiting our star. And if we see that edge on, so it starts to transit from our perspective, we can time these transits. One, quickly forward. Two. And we see the planet at the same time every time. So we can predict exactly when it appears back in front of the star. Now we're going to add another planet to the system. So here's our alpha planet. And if we tilt again, so we see the transits. And we're going to look again at the transit of the inner planet and start timing it. And now what we see is the time isn't always the same due to the gravitational tug of this second planet. And the larger the variation, the bigger the planet mass. So it's the difference between running around your running track with a Chihuahua versus a Great Bernard. So the Great Bernard is going to have more of an effect on your lap time. So TTV actually gives the mass of the planet in addition to the planet's physical size. So what did we see with these 7 worlds? Well, let's look at radius as a function of Earth mass. And we see we have 3 planets with almost exactly the same size as Earth, and 3 planets with a slightly smaller size than Earth, and 1 slightly larger. And if we look at the masses, we have anything between 40 and 140 times the percentage of the mass of the Earth. So we have 7 roughly Earth-sized planets. So here is the question. Does Earth size mean Earth-like? Well, what else do we know about this system? Now, on Earth, a year, so our lap around the sun, takes approximately 365 days. If you were on Mars, it would take 687 days. If you were on Venus, it would be 225, and Mercury would be 88. The TRAPPIST planets, the one furthest from the star that's going to take the longest orbital time, will take 20 days. 12 days, 9 days, 6 days, 4, 2.4, and 1.5 days to make that orbit. So if these were around our sun, all of these planets would sit inside Mercury's orbit. So does this mean that the TRAPPIST-1 worlds are in fact lava worlds with melted crusts of magma? Well, something, fortunately, saves us. And that is that TRAPPIST-1 is very dim. If we were to compare the size of the sun with a basketball, then TRAPPIST-1 only has the size of a golf ball. And it has only 1,000th of the sun's brightness. So that means you can afford to be a lot closer, but not that much hotter. So if we compare instead the amount of radiation the planets receive, then the amount of radiation that we get from the sun over Venus, Earth, and Mercury is approximately equal to the amount of radiation received by planets C, D, E, and F. So very similar radiation for these planets. So what about water? Well, when we talk about water, especially with exoplanets, we typically talk about something called the habitable zone. And this is the location where an Earth-like planet could have water on its surface. So you could imagine taking the Earth and giving it a push towards the sun. And at the point where our water and our oceans become steam and evaporate, that is the inner edge of the habitable zone. Conversely, if we took the Earth and pushed it outwards, then there comes a point where the oceans freeze. And that is our outer edge of our habitable zone. So if we look at the planets around TRAPPIST-1, the same habitable zone exists here over planets E, F, and G. So does that mean we have 3 planets with water? Well, not so fast. We have to look at the small print of this habitable zone contract. The habitable zone is defined as follows. The habitable zone is where an Earth-like planet can maintain liquid water on its surface. And the small print here is Earth-like. So if you have a planet that is not an exact Earth clone, it maybe has a larger mass, a smaller mass, a different atmosphere, different rock type, there is no guarantee at all that it will have water inside the habitable zone. Indeed, of the exoplanets we've discovered, we found roughly 5 times as many gas giants like Jupiter inside the habitable zone as we have planets that may have a rocky surface. So then the question becomes, these 3 planets, they're Earth-sized, but are they Earth-like? Earth-like enough for the habitable zone to be meaningful? So with exoplanets, we typically know 2 things, and this doesn't just apply to the TRAPPIST-1, it applies to all exoplanet discoveries. We typically know either the planet radius, if it's found through the transit technique, looking at that light dip, or we know the planet minimum mass if it's found from that red and blue Doppler wobble. And occasionally, like the TRAPPIST system, we know both. So we know something about the planet's physical extent. We also know how much radiation it receives from the star. Now, the small print here is this is not the same as surface temperature. And the warning to that is in our own solar system. So Venus receives roughly twice the amount of radiation that the Earth does. And if you were, therefore, to make a guess at the surface temperature of Venus, you would guess 27, 30 Celsius, which is 90 Fahrenheit, maybe? Anyway, it seems very pleasant. We should go there for a beach holiday. But in fact, that is not true of the surface of Venus. The surface of Venus is at 460 Celsius, and it doesn't even really matter what that is in Fahrenheit. It's just ridiculously hot. And the longest a spacecraft has ever survived on the Venetian surface is less than 2 hours. And the difference is Venus's huge atmosphere, which we cannot tell currently at a distance when we look at exoplanets. So we don't know anything about the surface conditions of these new worlds we've found. And what do we need to know to say, yes, this is Earth-like? Well, most certainly size is important. If you have a planet that's Jupiter-sized, we can be pretty sure that it's not going to have a solid surface. It's not going to be Earth-like. So you definitely need to be in the ballpark of the Earth's radius and mass. But our planet also has a protective magnetic field, and this protects us from the flares from the sun that would strip our atmosphere. Instead, charged particles from the sun get caught safely in our magnetic field and come down as the northern and southern lights at our poles. Occasionally, we might have some damage to our GPS systems, but the surface of our planet is mercifully not sterilized. Volcanoes. So you might think a planet with no volcanoes sounds like a rather good idea, but it turns out they're rather important for our atmosphere. During the early Earth, we needed volcanoes in order to get the atmosphere that ultimately developed life. And indeed now, it's one of the ways that greenhouse gases are controlled over geological timescales. Rock type. Again, it's how we control our greenhouse gases over geological timescales and how our planet managed to maintain very good conditions for forming life for so long. The presence of water. Just because you can support water, there's no guarantee you have water to support. So as I mentioned, the Earth formed inside the ice line. This may have meant it was actually formed as a dry planet, and that our water could well have been delivered later on by icy meteorites scattered inwards by the giant planets like Jupiter and Saturn. So if you have a different planetary system without those big beefy planets outside you, do you get a scattering of icy meteorites to deliver water? We're not sure. And plate tectonics, our crust, our surface, is divided up into chunks. And these chunks allow our planet to cool, which helps generate our magnetic field. And when we observe a planet around another star, we only know about the first 2. We don't know about any of these other effects at the moment. So it takes a lot to be like Earth, and we don't know very much about any of these exoplanets. However, in the case of TRAPPIST-1, unusually, we do know one other thing. The planet orbits of TRAPPIST-1 are in resonance. And that means that if you look at the time for each planet to orbit the star, you see something rather interesting. In the time it takes for planet B to orbit the star 24 times, it takes planet C orbits 15 times. 15. Not 15.5, not 15.3, not 15.12783. It's an exact integer, or very close to it. And the pattern continues, 24, 15, 9, 6, 4, 3, 2, 1. Very close to being exact integer ratios of one another. So how does this happen? It seems like a bit of a coincidence. So what we believe happens is that if the planets are born far from the star, and they go through this migration process to come further in, if you have multiple planets doing this, and their gravity pulls on one another, they can end up locked in these resonance positions. So as they both migrate in, their orbits at some point will sync up to exact ratios. And this turns out to be very stable. So once you hit this sweet spot, you tend to stay there. And then the planets continue to migrate in with these exact ratios as their orbit. And you might be like, well, cute, but so what? The point is that if that happened to these planets, that means the planets started here, further away from the star, behind the ice line, and then ended up here. This would mean that they formed with a lot of ice. And so maybe as they moved closer to the star, this may have melted to become a global ocean. So our other option, instead of a lava world, it could be that the TRAPPIST-1 planets have a huge amount of water, and they're actually water worlds with no exposed land at all. So this is a beautiful graphic by NASA, and if we go below the atmosphere, this is how we might picture a water world. So this then brings us to the obvious question. Are water worlds habitable? I mean, water and life are intricately associated on Earth, so is more water better for life? Well, the shorter answer is we don't know. We've got no analogue in our solar system to go and explore which has a surface global ocean. However, we have some reason to be slightly skeptical. And it comes down to the carbon dioxide in our air. So if we didn't have an atmosphere, the global temperature of the Earth would be -5 Celsius, below the freezing point of water. However, because we have an atmosphere and it contains these greenhouse gases, we're able to trap heat effectively and brings our global temperature to about 15 Celsius. And exactly how warm our planet gets can be controlled by geology through what we call the carbon cycle, or sometimes the carbon silicate cycle. So here, carbon dioxide in the air dissolves in rainwater, comes down as slightly acidic rain, it reacts with the rocks and forms a solid. This gets swept into the ocean, and it eventually gets returned to the atmosphere through volcanoes. Now, the process is very slow, so it doesn't really protect us against man-made increase in greenhouse gases. But it does protect us over slower moving changes. For example, in its early years, the sun would have been much cooler. And during this time, our Earth should have been too cold for life. But we have evidence that it wasn't. And one of the possibilities is that this process was able to change the amount of greenhouse gases in our atmosphere. So if the planet was colder, this reaction with the rocks would have slowed down, because chemical reactions slow when it's colder. But we still would have been spitting out carbon dioxide into the atmosphere. So the amount of greenhouse gas in the atmosphere would have risen and given us a thicker thermal blanket. And this allows us to have a lot more time in which life can develop on Earth. But it needs land. So if you have a global ocean, can you have any kind of carbon silicate cycle? So could a water world actually regulate its temperature? If it couldn't, it has two main effects. The first is your habitable zone, which I presented as a broad band, shrinks to a narrow point. Because the reason ours is a broad band is that our carbon cycle can adjust slightly our atmosphere to allow us to manage in slightly warmer areas and slightly colder areas. If there's no way of adjusting the thermostat of the planet, the radiation you receive from your star needs to be bang on perfect. So you get a very narrow band for that habitable zone. Secondly, because you can't buffer against the star increasing in luminosity, you have a much shorter time for life to be able to develop. So does that mean it's curtains for any water worlds? Well, not necessarily. It may depend on ocean depth. For example, if the ocean is shallow enough, you can still have a carbon silicate cycle with the ocean bottom. It's not as good because the ocean changes temperature much more slowly than the atmosphere. But it's maybe not impossible. If the ocean gets very deep, then the chances are the pressure at that ocean floor will rise so much you'll form ices. And these ices will completely seal off your rocky core from your ocean. And so it won't be able to produce any kind of thermostat at all. So this always leads to the question of, can we go and check these planets out? Well, our closest exoplanet is the one orbiting Proxima Centauri. This is our nearest star, so it's our nearest possible exoplanet. And it's 4 light years away. Now, our fastest spacecraft is Voyager 1, which is currently at the edge of our solar system. If Voyager 1 was pointing in the right direction, which it isn't, it would still take it 75,000 years to reach Proxima Centauri b. Now, there are some other ideas in the pipeline. For instance, there's Project Starshot, which is an idea where we could use lasers to send very, very, very light spacecraft to great distances reasonably quickly. But it's futuristic technology, and we don't know yet whether it's at all feasible. However, all is not lost. There are a couple of really, or more than a couple, several really exciting missions coming up that are going to tell us a lot more about these exoplanets. So as a planet transits across the star's surface, some of that starlight is going to pass through the planet's atmosphere. If we can spot that, then we will see a fingerprint that marks out the gases in the atmosphere. So the light passes through the atmosphere. Particular molecules in the atmosphere will absorb certain parts of the light spectrum, and so they'll be missing when we observe them on Earth. And based on those missing light waves, we can tell what gases might be in the atmosphere. And this gives us our first hint at geological processes, and maybe even a whiff of life. So, obviously, being a Space Telescope, I have to mention that one of the major instruments that we'll be looking for this is, of course, the James Webb, which is due to launch in 2019. But there's also ESA's, the European Space Agency's Ariel mission, which is hopefully to go up in 2026. So this is going to be very exciting. And just to end on an utterly shameless pitch, as Frank mentioned, my book comes out today officially in the US. It is full of truly awful planets. I mean, there are the hot Jupiters, there are Tatooine worlds around 2 stars, there are rogue worlds that have no star at all, there are planets with seas of lava and tar. So really, whatever your favorite way to die horribly is, you'll probably find it in the pages of my book. So if you're at all interested, I've put some little cards here just to remind you. Please grab one. And thank you very much. Questions?
All right, so I'm sure we have a few questions. I see in the green back there. No, that was you.
It's me, okay. You know, you're talking about all these terrible planets. What about ours, which is, you know, sort of so coddling almost? What is your knee-jerk reaction when people talk about like a Gaia hypothesis, where it's like a system working together to maintain this balance?
Living organism.
Yeah, one giant organism.
Okay, so I'm going to repeat the question for the online audience. So the question is, what is your opinion on the Gaia hypothesis that considers a planet as sort of being an entire organism and such?
So the idea that perhaps that life requires, there's interaction between life and the planet. I would say I definitely agree. So we don't quite know. One of the issues when we talk about life outside our planet is something called the Fermi paradox, which is basically summed up as where is everyone? Like, why have we not found advanced alien civilizations talking to us? And the question is, where is the bottleneck? Is it that life is very hard to start? Maybe you never get a planet with the right organics to start life. Maybe life develops, but in fact, it dies really quickly. Or maybe that you can develop life quite easily and actually it thrives, but it just never becomes intelligent life because it's not selected for. Those sort of options. And one hypothesis put forward by Charlie Lineweaver was actually what he calls the Gaia bottleneck, where he says that you have to not only form life, you have to form it fast enough that it can actually change your planet's environment to self-sustain itself. And so that's the idea that in the early stages of our Earth, the carbon cycle that I mentioned before was not sufficient to actually protect our planet's atmosphere and keep it temperate enough. But because we were able to form life, it was able to replace the carbon cycle.
Obviously, the aliens are trying to drown out her talk because she's revealing too many secrets.
Clearly your question
I
was
apologize,
far too
folks. Those of you who've been here know this has absolutely never happened before. In my 17 years, we've never had that kind of noise. Let's see. So,
Should I just summarize what I just said?
sorry. I will also note that we just had some major work done on the auditorium. I don't know if you noticed the projectors are 4K and other things, and the audio system was updated a little bit. So I apologize. This is the first live event to test out the system in detail. So you can see that it is being tested out. Okay, so back to what you were saying.
So even though obviously external forces tried to stop me answering this question, I would say that I would consider life as to be definitely part of the planet. I think when we talk about origins of life, we also have to talk about planet formation, and they are intricately connected, yes.
Okay, in the black over there, yes. So the question was on the stellar type of TRAPPIST-1. Is that what you're asking about?
Yes, it's a red dwarf.
Yeah, it is a red dwarf.
So red dwarfs are interesting. They're good and bad. Why is it always on my answers as well? So, yeah, TRAPPIST-1, red dwarfs have pros and cons. One of the pros is that being very small and dim stars, it's much easier to find planets circling them. And indeed, Kepler's successor, TESS, is going to be focusing on red dwarfs for exactly this reason. However, they're also extremely rambunctious when they're young, and they are prone to a lot of stellar flares. And it is possible that planets around red dwarfs may become sterilized, because during this early phase in the star's evolution, it just might have nuked everything that might be developing on the planet. At the moment, we just don't know. The interesting thing about TRAPPIST-1 is if they genuinely did this migration, it might just have saved them, because they would have started further away from the star when the star was younger, and maybe that it would have got over its flares and awkward adolescent stage by the time the planet started approaching it.
All the way in the very back row there. Do you anticipate any ability, method, or technology that will allow us to see large moons around gas giants? Okay, so do you anticipate any technology that will allow us to see not just exoplanets, but also exomoons?
Now I'm going to start this answer and see if everything cuts off again. Yes, absolutely. So René Heller, who is an expert on exomoon formation in Germany, told me that he feels that exomoons is where exoplanets was at the start of the 1990s. We are on the brink. And indeed, there are active searches currently going on for exomoons. One of them is called HEC, which I've forgotten what it stands for, but it's using Kepler to look for moons. And the PI on that is David Kipping at Columbia University. And currently, Kepler is sensitive enough to find a very, very large moon. In fact, slightly larger than we believe would form around a gas giant, but could potentially be captured. Now, of course, if we find that Earth-sized moons exist, then we have a lot more real estate, because our gas giants are mobbed with moons. So if you imagine a gas giant in the habitable zone, then it's not habitable, but it might have a whole bunch of moons that are. Now, it's a slightly interesting game when you start looking at exomoons and habitability. In particular, they get multiple sources of heat, because they get the star, but they also get heat coming from the planet. So that may mean that if the planet is in the ideal spot to support liquid water, its moons may potentially be too hot. So it might be your ideal Endor or Ewok-filled moon would actually live slightly outside the habitable zone, with the planet providing that additional source of heat.
Okay, other questions? Over here.
If and when we're able to travel to Mars and do further exploration, is there something that you're hoping for if that happens that you're not learning from?
So what can we learn? If we are able to travel to Mars and explore it, what shall we learn that will enhance our knowledge on this subject?
So I think probably what most people would love to find is life of any kind, or even evidence that it had it. If we go back to this bottleneck idea of where is everyone, like one of the questions might be, does life just never start anywhere? I mean, that's possible, right? If we were to find a second genesis of life, that would probably imply that actually life is pretty easy to kickstart. Now, Mars isn't necessarily the best place for that, because it's sufficiently close to the Earth that we can share material. Indeed, there are even some theories that it's just about possible life originated on Mars and then came across to Earth. But we never found any evidence for life on Mars so far. And maybe more interesting area might be Europa. So as a moon of Jupiter, it has these deep subsurface oceans. If we were able to find evidence of life on those, I think we could be more certain to say this was an independent genesis of life. And therefore, life is at least easy to start, if not continue.
Okay, question down here.
Will the hot Jupiters eventually lose their atmosphere being that close, and why isn't our Jupiter hot?
Will the hot Jupiters eventually lose their atmosphere by being so close to the star? And why isn't our Jupiter hot?
So to answer the first question, some of them do. In fact, some of them come close enough that the star's gravitational field starts to penetrate that atmosphere and literally starts siphoning it off. We call that Roche lobe overflow. And we've also seen evidence of some hot Jupiters rapidly using their atmospheres. So certainly for some of them, if they're close enough, yes. Now, the question of why our Jupiter isn't hot is a big mystery. So the idea of migration was not actually invented when we found hot Jupiters. Indeed, the idea had been around since the 1980s, and we knew that it was possible that this migration process could occur. But we looked at our own solar system, didn't see any evidence for strong migration, and therefore it was assumed that it either didn't happen or it just wasn't a major player. Now we've discovered all these exoplanets, we realize it's a major sculptor of exoplanet systems. So then the question comes, are we weird? So what people think happened with our gas giants is that Jupiter was formed, and indeed it did start migrating, and it started to munch its way towards the inner solar system, which would have not looked good for Earth. But as it was doing so, Saturn formed and caught up with it as it started its own migration. And at that point, the gravitational pull of the two planets together caused a U-turn that we call the Grand Tack model, after the sailing turn where you turn the boat around. So the two planets moved in together. They actually did a U-turn around about the position of Mars and moved out. And it's one of the explanations we have for why Mars is so small. Because naively, we would have thought further away from the star, where the star's gravity is a little bit weaker, you should actually be able to build a larger planet. But instead, we have a really squiffy one. And it's possible that it was Jupiter just marched right in there, ate up all the building material, and then left. Now, whether this is common, we don't know yet, because it's harder to see planets at Jupiter's distance around other stars. As we start to see more planets that are further out and get a more complete picture of planetary systems, I think we'll get a better idea about whether this grand tack system is common or whether actually we have a very unique system.
Okay, question in the center there.
And as kind of a follow-up, is the word migration indicates that it's still moving. Could these hot Jupiters eventually go in, actually hit the star that they're formed?
So does this migration process, can this migration process end with the planet being absorbed by the star?
So, no, mainly. So right now, for migration to happen, you have to have the gas disk still circling the star. And after about 10 million years, the star vaporizes it. At that point, planet migration, due to the gas disk, stops. There is also normally a gap at the disk edge. So the planet could go up to that gap just before it reaches the star and also stop because there's no gas that side. So in terms of gas-driven migration, it shouldn't throw the whole planet into the star. There should be some kind of stopping mechanism. Now, exactly what stops the planets, we're not certain, because we don't see planets all at exactly the same distance from the star, which would suggest it was just stopping at the disk edge. Instead, we see hot and warm Jupiters that obviously seem to have migrated but stopped at different distances. And we're still not entirely sure why that happens. There's different ideas for these planet traps that can cause, for instance, sharp density gradients at the ice line that can slow a planet down and hold it for a bit. And obviously, the gas disk can evaporate at slightly different times and end up effectively beaching the planet. But for the hot Jupiters we found now, because the gas disk is no longer there, they're safe.
Okay, one over here.
When you make comments or observations about orbits on distant worlds, it seems to me we're making the assumption that we're using Earth time. But if time is relative, is it possible that time is very different on these different worlds and has a completely different, I don't know, if a second is 10 times longer than it is here or whatever, that then for the impact would be different?
Okay, so the question was, when you talk about these other worlds, you're referencing Earth time. Is there a way for time to be different that on these other worlds where the unit of measure is different or actually experienced different? I guess that's the question.
Yeah, so I mean, Interstellar movies are obviously examples of time moving differently on other planets. But I mean, it doesn't really affect us because we're not on the planet, so we see everything in Earth time. So.
Yeah, we're all measuring it from our point of view, so the measurements would be the same. Down here.
In other solar systems, is there a minimum distance from the star and a maximum distance? Is that kind of area set?
A minimum distance for what?
From of a planet from the star and a maximum distance. Is that area where planets form?
So the question is, in other solar systems, is there a minimum distance from the star and maximum distance from the star for planets?
So the protoplanetary disk is typically between 1% and 3% of the mass of the star. And for that build-up process from dust through to planets, that controls where you can form planets. However, it does not control where the planets ultimately end up. Because in addition to this gas migration, which would occur still within that disk, there's also scattering. So if you have multiple planets in a system, they can gravitationally pinball each other out of the system. So in our own solar system, we see evidence for that happening in small objects. So for example, some of our long-range comets come from an area we call the Oort cloud, which is a huge distance away from us. And it's thought that objects there couldn't possibly have formed there. They must have formed much closer where our normal planets are, and then been scattered gravitationally by planets like Jupiter and Saturn in this kind of gravitational pinball game. And when we look at extrasolar planets, we do sometimes see planets that are far more distant then there should have been a decent amount of gas and dust in existence. And we genuinely believe that that is beyond the edge where we expect planet formation, and they probably didn't form there, but instead a scattering event lobbed them further out. So as a result, we don't have a hard edge to where we expect to see a planet, not because we believe it could have formed infinitely far, but just because the scattering process can then later send it a lot further out.
Okay, do we have one last question? Doesn't look like it. Okay. So, all right, we'll give you the question. Okay, go ahead.
Question, how do you feel about, the protection of the Earth and what we are doing to it? I mean, I think it's so crucial, I really do.
All right, so the question was, since you're studying all these other planets, how do you feel about the protection of our own planet and how we might be treating it?
So I'm going to answer that with, I believe, a slightly controversial statement and say I loved Interstellar, the movie. And the reason I loved it is that it got hold of one of the things I hate so much, with this idea that Earth-sized means Earth-like. In Interstellar, you saw Earth-sized planets that were not remotely Earth-like. Once more, they were incredible distances away, so much so that the only way possible of ending that movie was to go so completely crazy that the lead character had to fall into a black hole. And I think that tells you that even if life is common in the universe, even if there are no bottlenecks, even if the Fermi paradox is not a thing and you can develop life on all these worlds, we may never, ever reach it. And that means, as far as we're concerned, we've only got one Earth.
I know. It's precious.
Okay. All right. We will see you again next month in December for the Public Lecture Series. Let's give Elizabeth another hand.
Yeah. No.